Hello everybody, this is Cameron Snow with Danomics.com. In this video, we're going to be going over some of the theory behind calculating water saturation. By this point in the workflow, we've already calculated our clay volumes, we've done our TOC analysis. We then went in and we calculated a porosity, where we then used the clay and TOC volumes to correct that down to an effective porosity. And now we are going to do the water saturation calculation. So in terms of water saturation, there's a few different methods that are available to us. First of all, Archie's equation. This is the method that Gus Archie came up with in the 1940s. It's simple, it's easy to understand, and it works really well if you're looking at traditional sand shell systems. And it can be done using either an effective or total porosity. So sometimes you'll hear people talk about an Archie or an Archie's PhiE, and that's just whether or not you use the effective or the total porosity. And ideally, you're using this in systems that have very little clay, so those two values are almost identical. We have the clay resistivity models. These are things like Simandoux, modified Simandoux, and the Indonesian methods. These add a layer of sophistication, and they were really designed for working with zones that have a higher shell content. So these methods take into account the fact that shells are often conductive. And so we'll look at the shell resistivity and we'll set that as a parameter in these methods. And then finally, there are some models like the dual water models that try to take into account the resistivity of bound water and the clay fraction of the rock. These are more sophisticated models, but at the same time, they have some parameters such as the resistivity of the bound water, which can be quite hard to get a calibration on. So just to start off, let's look at Archie's equation. So very simple, we have the formula here. It's the water saturation is equal to A over phi to the m. So A is the tortuosity in the rock. It's supposed to represent the flow path in the rock. The porosity can either be the effective or the total porosity. M is the cementation exponent. And then that's multiplied by the water resistivity divided by the deep resistivity from the well log. And that's to the 1 over n, where n is defined as the saturation exponent. So like I said, this performs well in clean intervals. And if your V clay is very low, i.e. approaching 0, it yields the same answer as the clay resistivity models like Simandoux. However, in shaly intervals, it gives you higher saturation in your shells, which, depending on what you're analyzing for, sometimes this can be the desired effect. Other times it may not be. And this is a method that, even if you end up not using it a lot, it is a method that you must know because it is the most widely used method that's out there. Okay. So as I said, here are the exponents. So generally, in terms of these exponents, so m and n, we often default these to 2, but both these properties can be measured in the lab. So those are things that you can try to get a better feeling for through lab data. Tortuosity, although that can be calculated, it requires extensive testing. And then RW, this is one that is this is one that you should really have for any well that's produced. It's the resistivity of the formation water. It is a very inexpensive, very quick measurement to make, and that is a parameter that hopefully you will have data for when you're doing your analysis. So one of the things that we'll use a lot is the Pickett plot. And you'll hear me refer to this plot a lot, and the reason why is because it is my absolute favorite plot in petrophysics. The Pickett plot, it allows you to effectively set RWM and visualize the effect of N within this. So the when we look at the axes, the y-axis is typically total porosity, and the x-axis is resistivity. You can choose whether or not to use a total porosity or an effective porosity. I typically use a total porosity, and I think that's most common in the US and in a lot of Europe. However, in some regions, such as Canada, you'll find that the convention is to use an effective porosity. That's just a slightly different interpretational style. Both methods can be viewed as equally correct. And generally, we'll try to filter down the data that we are displaying on the plot to only show reservoir quality rock. And you know what the real beauty of this plot is in the fact that it allows you to visualize so much. So let me just explain this. Hopefully you can see my mouse here. These lines that are running diagonally down and to the right, these are lines of constant saturation. So we have the 100%, 75%, 50%, and 25% saturation line. So any point that falls on this line is 100% water saturation. Any point that falls on this line is 75% water saturation, and so on. If you think about, you know, what does it mean when you have 100% porosity? Well, 100% porosity would imply that you have 100% fluid in your rock, and that means that this point up here, where we have the intersection of the 100% saturation line with 100% porosity, that would essentially tell us what our RW is. That's the formation of our resistivity water for 100% saturation at 100% porosity. That would be like measuring water. So that can tell us what our RW should be. The slope of this line is actually the M exponent, and the spacing between the lines is dictated by the N exponent. So you can quickly see the beauty of the Pickett plot here is it allows us to visualize SW, RW, M, and N all in one convenient plot, and that's what makes the Pickett plot so powerful. So there are some things that we need to consider when we're doing a saturation. So you'll hear me talk about RW. This is the resistivity of the formation water. Like I said, we normally get this by measuring the salinity of produced water from samples. So, you know, you collect these samples of the wellhead, you send them off to the lab, and they'll measure it and they'll tell you in RW. So a few caveats here. First of all, you need to make sure that this sample actually represents formation water and isn't something like your completion fluid, which can be a concern if you capture your sample, especially very early in the flowback phase after a frac. So, you know, the RW and salinity, they essentially go hand in hand. The one thing I will say is salinity is something that is a measured property regardless of state, whereas RW is temperature dependent. So this means that, you know, since we talk about RW in the equations that says salinity, it means we need to establish a temperature profile. There's a lot of ways we can get a temperature profile. You can actually measure the temperature directly from the logs. You can you know, you can look at the bottom hole temperature in a well, and then calculate a gradient back to the surface temperature, or you can put this together through regional knowledge. And of course, you know, your temperature is a function of depth, which means that RW in many cases is a function by depth. So this is not something that's a constant over the entire wellbore. So now we're going to look at a few of the other methods that are out there. So for example, the Simandoux method. As you can see, this equation is a bit more involved. And the main thing here is that it has this resistivity of clay component, and we would generally establish this resistivity of clay through a cross plot of resistivity versus our clay volume. And we would essentially kind of fit a trend to this and extrapolate out to higher clay volumes. Now, some people would take the resistivity kind of here at the highest observed V clay method or V clay values and say, okay, well, it looks like we're at a value of 2, 3, about 4 here, or some interpreters extrapolate it out, and in this case, you'd be at a value of around 2.5 to 3. It's really kind of interpreter's choice here, and this is where differences between interpreters start to arise. So when do we use something like the Simandoux method? We use this method when we have shaly sands. So for example, if you're working in an area that's let's say a lower shore face sand where you have let's say maybe a roughly equal amount of sand and shale interbeds. Maybe your sands aren't clean, maybe they're higher shale beds. That is when you would use something like the Simandoux equation. And there are other methods that are available, such as modified Simandoux and the Indonesian methods. Finally, here we just want to show you the equation for dual water. And the main additional parameter here is we have the parameter RWB, and this is the resistivity of the bound water. So, the issue of bound water is that this is supposed to represent the water that is bound up in your clays. The problem is this is something we can't really measure in the lab. So I always think we need to have a good justification for choosing something like the dual water method over Archie or Simandoux's. Okay, when it comes to how we calibrate this, like I said, RW can be measured from produced water. It's low cost, it's quick, it's easy. We can measure our M and N exponents, but these need to be part of a core program. They are expensive and they are time consuming. And then we can measure SW itself. So you can do this via things like capillary pressure measurements. You can do it through the Dean-Stark method. You can do it through crushed rock methods, etc. So there's a number of ways that we can calibrate ourselves on this. And it's important to be calibrated, but I would say the most common measurement and the easiest measurement that you can acquire to really reduce uncertainty is RW. So that's something that you should really do right away. So now I'm going to jump over to our software here, and we'll take a quick look at what it is we are we're working with here. So we're looking back at the same intro project, and now we are going to be setting the water saturation profile in this well. So just a reminder of what our well looks like here. We've got and mainly in this interval we have combination of a mix of sand and shales, a lot of lower shore face. And we do have a couple of organic shales here in the Niobrara and in the Mowry formations. As we can tell from looking at our neutron density log, this is a relatively high clay system. So what we'd want to do is a couple of things here. First, we would probably go through and we'd want to set our parameters. And so here we have our Pickett plot. And I just want to explain how we kind of use a Pickett plot. So starting off here, we always, when we do a Pickett plot, we generally want to filter this down to reservoir quality rock. And so I'm going to say at effective porosity is greater than, let's say about 4%. And I'm going to say I want our V clay to be less than or equal to about 40%. So, and you'll notice what happens is a lot of the data down in this area will be filtered out. Okay, so we've got that. There you go. We can see that filter took place there. A little bit of lag here as we're recording it. And now this 100% line, if we believe that we have some wet sands, we want this 100% line to essentially go through our data here. So we want it to go through the data trend, and we want it to go through the kind of the very left edge of the data to really represent what is a wet sand. And so, there's a couple ways you can do this. So one, you can adjust this by changing parameters. So, let's say that we knew we had our RW and it was measured at 0.25. So 0.25 ohms. And what we would see is when we do that, now this 100% line is going through kind of the middle of the cloud. Well, what does that imply? That implies that everything on this line is 100% wet. Well, everything to the left of this line is would be technically greater than 100% saturation. Now, sometimes this is what happens. It's not that it's actually greater than 100%. This is just the way the data plays out. But in many cases, this means you need to do something like you need to adjust your M. So M, once again, controls the slope of the line. So maybe we adjust our M value down a little bit. We reduce the slope of that line. And now we see that this 100% line is running through the left edge of the data here. So this would be saying that, these sands that are right on the line are now 100%. And, we see that we get saturations in this well that are predominantly between 100% and 50%. There's very few points that are less than that. Now, you may be wondering, what do you do with N? There are kind of two schools of thought here. So a lot of times you'll hear people say that M is equal to N unless proven otherwise. Or you'll hear some people say that N is equal to 2 unless proven otherwise. So 2 is kind of the default value from the initial empirical studies, and that has held up relatively well through time. So that's always a good value to go with. But there have been a lot of studies that have shown that M and N tend to, not exactly match each other, but they are relatively close. And so, in this case, we set our M at 1.8. Now we set our N value at 1.8. When you set N at 1.8, it decreases the spacing between those lines. And so that, therefore increases your, it'll decrease your saturation, it'll increase the hydrocarbon saturation. And so that is how we set this. Now, ideally, you would have done some tests on your formation. You would have established what M and N are through your SCAL program, and that's how you do that. Now, if we switch this to Simandoux, one of the things we'll notice is that we now need to set a parameter for clay resistivity. And as part of that here, we have our clay resistivity cross plot. We need to go clear out that filter that we had in there, because now we're actually more interested in the higher clay fraction of the rock. And if we look at this, you can draw kind of a trend through here. So you kind of imagine where you want it to go, and you could say, well, we're at a value of 1 to about 3, between 3 and 4 ohms. Maybe if you extrapolate that out, you could just say 3 ohms on its own. So in this case, you would set the clay resistivity to about 3 ohms in this interval. So that's how you would establish that parameters. You would do this through the V clay resistivity cross plot. Okay, so that is essentially how we do a saturation calculation. I know we spent a bit more time in this in this video going over kind of the ins and outs of the Pickett plot and looking at some of the equations, so especially Archie's in a bit more detail. Um, but you know, that's really uh, you know, important for the saturation. I mean, you know, there's a handful of parameters here, and this is really what separates uh, a good petrophysicist or log analyst from someone who just has a little bit of knowledge. You know, it's actually one of those things where I think if you're doing a job interview and you're talking to someone and they ask you about log calcs, you can always use the Pickett plot as a way to, one, explain concepts, but also to really tell who knows their petrophysics and log analysis, and who you know doesn't. So it's something that's it's a really important calculation. Obviously, saturation will, you know, we'll take that, we'll combine it with the porosity, and that's what we'll use to start calculating things like our hydrocarbon pore volume once we get into the volumetrics. Okay, I hope this video was useful to you, and we'll be having some more videos come out as part of our educational series. So I'm looking forward to it. Thanks. Goodbye.